Soma.
Yeah.
One second. One second.
Participants, shall I start our session? I hope so. Participants,
yeah, you can start, please. You can
yeah,
start.
yeah, fine. Thank you, sir. Yeah, fine. So the last session, actually, we are much discussed about the ML model, how the ML model is exactly working. Okay. At last, if time permits, I will explain the entire process. Okay. Because this is not our exact area what we have to cover in this session. So we uh, just go through all the mathematical concepts one by one, and along with that I try to maps our today's session topics, right? One is a dimensionality reduction. Today we will going to discuss. So instead of a decision tree, I try to cover the naive base today now, because the naive base is actually planned today only, but tomorrow we are having a ensemble learning. So decision tree is covered with the ensemble learning. It's actually quite easily grab the concepts. So because both are actually interlinked. Okay, I try to cover the ensemble learning and the decision tree and the tomorrow session. In today's session, I try to cover the dimensionality reduction and naive Bayes classifier and all the feature engineering concepts, and then we will discuss about the naive Bayes classifier text applications, the text processing, text classifications, and then sentiment analysis, right? Yeah. So in the case of a vector as a matrices, so we already studied about this. Actually, so we all are come across in the school days itself. So we are having two different methods. So row ekanal method and another one is a inverse matrix. So I am not going deeper into that. So this is actually we have to concentrate more on this slide actually. So the linear algebra eigenvector. So naturally what we have to do, we have to practically understand what is really happening in the eigenvalue and eigenvector. Okay, so let us consider for this purpose. I try to illustrate with this images. Okay, so here I am having a two vectors. One is a v1 and another one is a v2. Consider the first image, right? So in the first image, this is considered as a v1 and this is considered as a v2. Okay, so this is without in this particular representation, it covers the entire rectangle areas, right? These two vectors, it's entirely covered the rectangular areas so far. So what I am going to do now, I am going to apply some transform operations, some operations on the particular vectors. Okay, so after we are applying the shearing operation, some transformations we are done on the particular vectors. What happened? This is how the diagram 2 is actually the representation of after shearing. What happened is actually here. What is really happening here? The thing is, vector 2 is actually changed totally, whereas vector 1 is actually not changed, right? Because which means the magnitude is actually varied, but look at the direction, it is actually not varied. So that is, we can say it as that vector is, we say it as a eigenvector. Okay, so if we are having a bunch of features, we have to identify the potential feature for your application. Okay, most of the cases, the ML application is we are concerned with the regression and the classification application for supervised learning, especially, right? So far, so we need a features, very potential features for performing the efficient classification as well as the regression part. Okay, what exactly? So I hope so now you understand what is exactly the eigenvectors, right? So eigenvectors, it does not change the direction even if transformation is applied to them. That is the potential. That is actually the it tells about the potential of the particular features, right? And moreover, they are most sensitive part of the data set and can be used for the analysis purpose. So it gives the very, very potential features about that particular data, right? About that particular data. So if you take that particular data itself, we can easily exploit the model well, right? This is how the eigenvalue and the eigenvector works. So whereas the eigenvalue, it tells about the magnitude, whereas the vector tells about the directions, we can say, right? So what is the direction and what about the magnitude value in that particular direction? So the linear algebra application. So we are comes into the end of the linear algebra session. So here actually, I try to make you to understand about the importance of eigenvector. I hope so. So based on this, we are having a the complete session, like, you know, the dimensionality reduction. That is, we are going to apply a principal component analysis. In that case, we will see a more deeper into this. So in case of the linear algebra applications, I try to summarize some of the applications which is actually based on the linear algebra concepts. So the topmost one is a principal component analysis, for especially for a dimensionality reduction. It helps to increase the quality of data. So why we are actually very much important in the dimensionality reduction, I hope so you people are remember the block diagram, right? So what is really happening? What is our first step? We have to explorate our data. If we are not properly given a data, what happen? Even though if we are creating a powerful algorithm, will not give the solution for the solution for the real-time applications, right? So what we have to do, we have to try to reduce the dimensionality reduction in such a way we can reduce the manipulation cost. That's why we are performing the dimensionality reduction on your features, right? Moreover, we try to take the potential vectors from that particular features. So whatever we are having, so that is actually the total vector. It may be, for example, I am telling, if you are having 100 features for cancerous and non-cancerous classification. Okay, so while you are applying a PCA, what happened? Out of 100, which is actually the most potential features, it just identifies. So which actually a most potential features. Okay, so that is, we can say, so it is a principal component. So by using that principal component itself, we can give the very good classification performance, right? So we are trying to reduce the dimensionality. Also, we are trying to remove the redundant information. We can say it's because that features are not at all helps to improve the performance of the model, right? So far we are trying to ignore all the extra or redundant features, right? By using the principal component analysis. The another one more analysis is also there. One is a linear discriminant analysis. That linear discriminant analysis, why we are actually transformed from the PCA to LDA. Actually, LDA is actually more concerned while we are dimensionality reduction in supervised learning. Why? Because if you apply a principal component in that particular multi-class classification, what happen? It just anyhow it going to give a new eigenspace for our data, right? So during that time, what happened? The classes gets overlapped. So that overlapping is actually overcome by using a linear discriminant analysis. Okay, just I want to conclude the point. What is the exact drawback of PCA? Okay, fine. We will see later. Okay, and this is actually working with and applying the transformations on the pictures. So images. So based on the linear algebra concepts, we can easily apply the transformation. So many transforms is available in our linear algebra concepts. So can easily transform the images for the easy manipulations, right? And moreover, encoding of the data set. So so encoding and decoding techniques and all we will see in our feature engineering. Okay, so once if we completed all the theory sessions, I try to take all the file and I will show how to do the feature engineering, because that is actually the first step we have to do very carefully while we are doing a data analysis application algorithms, right? So next is actually singular value decomposition. So based on this singular value decomposition backend only, our PCA it actually works, the principal component analysis, right? And then the next one is actually latent semantic analysis for natural language processing. And moreover, it is used for the optimizations for deep learning models. Just now we are seeing, you know, so many deep learning models and the ANN models and all, it is actually optimized by using this linear algebra concepts, right? So next leg is actually multivariant calculus, right? So in that multivariate calculus, so in which way this particular calculus help us? So the predominant thing is it try to explore the data in better way. Okay, so this concepts, this particular representation, this makes the data in the potential representation. So in such a way, we can improve the efficiency of the model. So it helps to solving the problem of optimizing the machine learning model, as well as the real world problem uses for calculus for many operations, right? This is what, that is how we are using this multivariate calculus. Look at here, how fair this data is actually, it makes or it transforms into the normal distribution data. And very important point is, most of the ML algorithm plays a very good role while you are feeding the normal distributed data, right? That concept and all we will see in the feature engineering. And this is actually the differentiation application. So the differentiation is actually uh, much useful while it's breakdowning of the functions in the in-depth analysis, right? Moreover, it helps to find the sensitivity of the information. Look at this one. So which is actually the a good functioning and which one is actually the bad function? First we have to know that. So what is a good function? A function which is easily represented by the mathematical way or mathematical representation. So that is, we can say is it is a good function here. So by defining that particular functions, you can easily calculate the differential value of that particular function. Moreover, we can easily understand, okay, anyhow, so whatever the output is provided by the particular model, it should be follow this one. Okay, if suppose my model produces the function of exponential of x, so the output should be, it follows this curve. So that is, we say it is a good function. So this representation is possible by using this calculus. And this is actually the one of the famous example of where we are using the differentiation formulae. So where we are using exactly, so in the car speed distance calculation application, this is actually okay. So here a car is moving a distance with the certain speed, okay, along with the time. So this is actually the speed versus time, okay, regarding the car. So if we are finding the rate at which the car moves, and it turns out to be a acceleration. So if you want to identify that, so that is your motivation, means we need a calculus. So we need a rate of difference. We need to identify the rate of difference, right? So for that analysis, we need a differential equation or differentiation formulas. So this is how we are calculating the derivative of the particular representation or a function. We can given it as the f of x is equal to limit del of x tends to 0, where f of x plus del x minus f of x divided by del x. So this is actually the differential equation which is used to identify the rate of changes, that acceleration values. So what are all the rules which is used in your calculus? So here we are using two rules, especially in machine learning. So whatever the topics here I covered, it's especially we are used in the machine learning, right? So here we are used to the power rule. Okay, I hope so you people are know why we are using this, right? So the power rule can be applied on the variable, which is actually a consist of powers. Okay, they helps in making the equation solving faster and efficient manner. That's why we are using the power rules here. The next rule is actually the chain rule. This chain rule only, guys, especially we are used in the gradient descent algorithm. So gradient descent algorithm, try to calculate the error by using the chain rules. So back propagation, so related to back propagation, someone is actually asked. So that back propagation is actually we are doing through a gradient descent. Okay, so by using the gradient descent, actually we are doing a back propagation. The back propagation, it's a approach. Okay, so we are propagating the error from the load side to source side, right? So this chain rule only we are using for calculating the error of each and every neurons in your model. Consider if you are having a 10 neurons, so aggregated value only it comes out into the real world, right? If you want to calculate the error of each and every neurons, we have to use this chain rule. Okay, during that place we are using the chain rule. So partial differentiation.
Suresh, there is a question for you
Yeah,
from Surbhi Mageshwari.
yeah.
Sir, I have a question regarding sign language recognition by agent vector. I am working on a sign language recognition system, but not found any practical method of agent value. So could you tell me or share me any document how to find the agent value?
Eigenvalue.
In some sign language, something she says related to the
Okay.
sign language recognition in which she is applying for an agent vector and agent value. That's a core part of the question.
Okay, okay, fine, sir. Sir, this topic is actually we are covering in the practical session. I will answer it in that particular session. Okay. So while
Please
we
go
are,
ahead.
yeah, while we are showing the demonstration, I will explain all those things, how we are utilizing that. So I hope so. I covered the how, where we are using the chain rules. And here the partial differentiation. So where exactly the partial differentiation comes into the picture. So consider the car manufacturing company. It's actually you are a core responsible for the exterior design alone. Okay, but you want to improve the performance of the car. That is actually the task given by the management, right? So what you have to do, we can't change any engine, we can't change any internal part because we are only the exterior designer. So what we have to do during in that particular case, how we are calculating the total approach. So where we have to update, which department is going to update to get a better performance. Likewise, we have to analyze first of all, right? So what is our area from the outdate performance, how to improve the performance by using my exterior design. That is what we have to decide, right? Because we are a exterior designer, engineer. So we have a authority to do that particular part alone. So how we are actually calculating the what to say, the portion of errors and all. During this cases, we are using the partial differential equation. So what is really happening in your role? You are only going to change. Okay, so all other parts are, but the other peoples are going to, other people are not changed, they are going to be a constant. Fine. During that time, during that case, during this kind of scenarios, we are using this partial differential equations, right? So this is where we are using the partial differential equations. So you are an exterior designer, consider you are having a engine section, okay, power section, and then color painting section, and something your exterior section. So what you have to do, you right now you have to calculate the performance of the model by only changing your role. Okay, so you are going to be act as that means the value, the performance is actually uh, differentiated with respect to your uh, exterior part. We are all other thing is going to act as a constant at their time. Okay, fine. So during that time we are using a partial differential equation functions. So this is how we are doing. So we are considering the three different parts. Okay, so engine, color, and exterior. So what is we have to do? So first you have to differentiate with the respect to the function is respect to the engine. People are going to be a constant. The same way in the next section, what we next point what we have to do, we have to concern about the part y, and both the other than the two thing is going to be a constant. It's going to act as a constant. Likewise, for the complete differentiation, what we have to do, the f dash of f of x comma y comma z, we have to add all these three values. This is how the partial differential is actually works for our ML applications, especially in our ML applications. In our ML application, what is happening actually, the updation of the weights, weight parameters are there, you know, in the applications, in the classifier applications, or it may be a regression applications. Let us consider the multiple regression applications. The equations are given it as a, you know, y is equal to, for example, for my application, I consider a two features. So far, I can write this straight line equation it as y is equal to y, w naught plus w1 into x1 plus w2 into x2. So in the part, we have to differentiate with respect to w0 one time and w2 one time and w1 one time. Okay, this is how the partial differentiation is used to update these parameters. This is actually the, I listed the some of the applications which is used in our ML algorithm from the part of multivariate calculus. It is mostly used for the helps to find out the global maximum of the especially, okay, and moreover it helps to identify the uh, Hazen matrix. So by using that, we can minimize the error, and it is mostly predominantly used in the deep learning model, especially for the gradient calculation. And that is what the algorithm name itself here I actually posted, gradient descent method for optimizing the weight values in the CNN, right? So this is actually I planned to take it in the two part. So first part is the first linear algebra is covered in the top portion of the life cycle, and second portion is actually covered by your differential calculus, right? Because the partial differentiation and all, it's happened in your ML algorithm, right? And your uh, addition and that, sorry, your linear algebra operations and all, it's happened in your ML model. So next, the important leg is probability. So I hope so everyone know about this. Just I try to cover the basics, because today I am going to take two very important topic. One is a principal component analysis and another one is a naive-Bayes classifier. For naive-Bayes classifier, we need this knowledge about the probability. For the principal component analysis, we need a explanation about a eigenvectors, right? So first, I try to explain about the probability. So probability is actually measure of how likely an event will occur. For example, I say, I just rolling on a dice. Okay, rolling on a dice, it just gives us some values, some 6 or some 7 or some 1 is actually, it's a outcome, right? So that is actually, we called it as an event, right? So the probability is naturally is measured as a ratio of desired outcome divided by the total outcomes, right? This is how we are measuring the probability. Especially, for example, look at here, while I am rolling on a dice, you get a 6 possible outcomes, right? So each possible is actually only has one outcome. For a one event, it's only one outcome is possible, right? So each has a probability of 1 by 6, because total is actually 6. So the one outcome at a time, only one is actually comes. So probability can be calculated it as 1 divided by 6. Some of the terminologies which is used in this, I hope so you people are know the probability. That's why I am rushing up this concept. I am just trying to elaborate the simple example regarding the probability. And the probability terminologies is actually, we can say, is a random experiment, sample space, and events. So random experiment is nothing but an experiment or a process for which outcome cannot be predicted with certain. During that is, we can say, is because it is a random, we can't predict anything. So that is, we can say, is it is a random experiment. Whereas a sample space is actually the entire possible set of outcome of a random experiment is a sample space of S of the experiment. For example, I say, if you are rolling a dice, so we know we will get only 1 to 6, right? That is your sample space. The value 1 to 6 only, it's a possible, right? So that is that space is, we called it as a sample space. By event is, so one or more outcomes of an experiment. So while you are rolling on a dice, you get a one outcome, right? That is, we called it as an event. So types of event. So we have to know, especially while we are working with the ML models, right? Especially while we are discussing with the feature engineering. So this type of event is we have to know. Either there is a two type of event. One is a joint event and another one is a disjoint event. In a joint event, we have a common outcomes. For example, I can say a student can get 100 marks in a statistics and also 100 marks in the probability. So that is actually the joint event, right? In the disjoint event is actually, it does not have any common outcomes. In the previous case, it is actually the opposite of your joint event, right? So what happened, the outcome of the ball delivered can't be a sixer or wicket in your cricket. Okay, while you are seeing the match, the outcome of the ball, it may be a sixer or it may be a no ball also. We can't do, we are not having any, there is a no relationship between these two things, right? So that is, we can say it is a disjoint event. There is a no relationship exists between these two things. And also we can, very simple case, we can say is a man can't be died and alive. At the time, the both the things are not happened. It's a disjoint one. So probability distribution, especially, what are all the distributions we mostly concerned in our ML applications? Probability density function we have to know. And what is a normal distribution? Central limit theorem. So what is a probability density function? Equation. It describes a continuous probability distribution. It's called as probability density function. Am I right? Yes. So a graph of a PDF will have a continuous over a range. Look at this particular representation, the diagram. It's actually representing the probability density function, right? What is the second property of this particular diagram? An area bounded by the curve of a density function and the x-axis is equal, right? So area bounded by this curve, it's actually x-axis is equal. Whereas the probability that random variable assumes a value between a and b is equal to area under the PDF bounded by the a and b. Okay, this is the third property of your probability density function. By using this picture, we can easily interpret this three property. And similar way, we have to concern about the normal distribution. So most of your ML algorithm, it's working holds good only if the data is follows the normal distribution. Okay. So if you exploit such a data in your model, you get a very good accuracy as well as you get a very good performance from your model in even in the real-time application also. Okay, so a normal distribution is a probability distribution that associates with the normal random variable x with the cumulative property. So this is how the mathematical representation of the normal distribution. Most of the case we know that Gaussian and the normal distributions are quite similar, right? So why actually I am representing this one, guys? Here in this session I try to cover the naive Bayes classifiers, right? In the naive Bayes classifier we have three types: multinomial naive Bayes classifier, another one is a Gaussian naive Bayes classifier, and third one is a binomial naive Bayes classifier. For the Gaussian naive Bayes classifier, this equation is going to use to calculate the probability values. That's why I am showing here. And this is about nature of the normal distribution. So what we have to understand from this picture, generally the distribution has a mean. It's a determinant, that means it's a means 0 and the variance is actually unit variance, or otherwise we can say it determines the location of center of the graph. Okay, that is actually the mean value, and the standard deviation is determines the height of the graph, right? Sorry, it is not a height, actually width of the graph. Okay, the variance is actually deals about the width of the graph, and the mean is actually deals about the height of the graph. And the central limit theorem, it states that it's actually So what I am trying to conclude this particular central limit theorem, while we are doing some feature engineering process, we have to concern about this. That is why I am actually elaborated this central limit theorem here. Here actually it states that the sampling distribution of the mean of any independent data or a random variable will be a normal or nearly normal. Okay, so if the sample sizes are large enough, so what happened guys, look at here what central limit theorem exactly says. If you are raising the samples, so this is actually sample 1, this is actually sample 2, this is actually sample 3. What happened if we are raising the samples? So it nearly looks like your Gaussian distribution, or it follows the normal distribution, right? This is what it states your central limit theorem. So if it is a n equal to 1, so this is how the distribution is there. If we are raising the samples, what happened? At particular point, it goes narrowed. It's similar, it looks similar to the Gaussian distribution. That states your central limit theorem. So what are all the types of probability in your probability concept are utilizing for our ML applications? So marginal probability, joint probability, conditional probability. These are all the three different probability. It's available in the specific probability concepts. So we have to understand what is exactly marginal probability. So naturally, the marginal probability is a probability of occurrence of a single event. Okay, especially while we are going to cover a classification. Okay, so this helps us a lot. That's why I am explaining this particular base, and then we move on to the naive Bayes classification. What is a joint probability? So joint probability is a measure of two events happening at a time. Okay, some of the two events is going to happen, so you're getting a two outcomes. Okay, but it at the same time. Okay, what about this particular probability for this particular cases? That is, we can say it is a joint probability. Let us consider the scenario. I am going to here I am having a deck of cards. Okay, in that deck of cards, I am trying to take a one of the card. That card is actually ace as well as R10. So what is the probability of that? That is, we can say it as a joint probability, because totally we have a 4 ace. 4 as. Okay, so out of a 4 as, I have to take a as. So what is the probability? I am going to take a as R10. Okay, so that is actually a joint probability calculation. So we are comes into the very important or a crucial topic. It's regarding a conditional probability. So this is very important while we are concerned with the naive Bayes application especially. So the probability of event or outcome, it's based on the occurrence of previous event or outcome. Okay, especially the conditional probability of event B is a probability of the event will occur at the given that the event A has already occurred. Okay, so far we can given it as P of B by A can be written it as P of A by A and B divided by P of A. I hope so. You people are know what is this exactly. Okay, we are on to the naive Bayes classification. We will see that. So it's a conditional probability representation for the two events. We already discussed what is a conditional probability definition, and then this is a mathematical representation of the conditional probability. So one thing you have to understand, if both the events are dependent event or independent event. If it is a dependent event, it is given it as probability of A and B divided by probability of A. Whereas it is an independent event, the probability of B by A can also be given it as a probability of B, or it is equal to the probability of B. That is, we have to concern. So this is actually the Bayes theorem. This is a very important. This theorem only is going to help us to do the naive Bayes classification. We will see how the naive Bayes classification works. Okay. So this naive Bayes theorem help us to classify the documents, especially the numerical events, especially the numerical data. It also processed both the continuous, categorical as well as the binary data. Okay, just now I said, we are having a 3 different types of naive-Bayes classifiers. For the continuous, we have to use a Gaussian. For a categorical, we have to use the multinomial naive-Bayes, especially for a text classification. While we are doing a text classification, we have to use a multinomial. Whenever your data set is having a binary data, zeros and ones, during that time you have to use the binomial naive-Bayes classification. So this is how the definition of the Bayes theorem, it shows the relationship between one conditional probability and its inverse. That means it's a maximal likelihood function. I hope so you people are know this, right? So probability of A given B, it can be defined in terms of probability of B given A, it's defined it as a maximal likelihood function. This is a likelihood function ratio. We have to maximize this ratio, right? So far, the probability of A is nothing but a prior probability, which is already known. It is already happened one, right? And then divided by probability of B, right? So we have to calculate the posterior probability for the event, okay? For the occurrence of a given B. This is, we can say it is a posterior probability, okay? So this is how the Bayes theorem works. So if you want to calculate the posterior probability, we need a maximal likelihood function as well as the prior probability and divided by the evident. That means your P of B. So this is actually I try to covered in the while I'm taking a session in the Bayes theorem. Okay. So what is a probability? That means a Bayes theorem examples actually where we are using this Bayes theorem actually. So this is actually very simple application where we are using the Bayes theorem. Suppose you are running a clinic, okay, where you are test a patient has a liver problem or not. That is actually you want to know, okay. And the probability, the prior probability around the patient having a chronic liver disease is a 10%. That is P of A is actually 10%. And the probability that the patient drinks, it's actually the 15%. That is your probability of B, right? Suppose the probability of that they drink even though they are having a liver problem. How to calculate that one? That is nothing but the P of A. A is nothing but already he is having a liver problem, a given drinking. That is your B. Okay, so we have to calculate P of A divided by B. Am I right? So this is how we have to calculate the probability, posterior probability by using a Bayes theorem. Okay. Hence the probability that they do have a liver problem is calculated now. So probability of B given A can be given it as 33.33%. So people who all are coming into the hospital, they may have a chance, 3% of chance they may have a liver problem, right? This is how we are summarized from this application. So these are all the some of the applications which is covered by the probability in our ML models. So it is actually used in the classification wherever we are doing a decision making operations, guys. In your ML model, wherever you are doing some decision making operations, in that particular place, probability plays a predominant role, right? For example, I say in CNN we are using a softmax. So softmax is actually calculating the probability of each classes. What are all the classes we are given in the data? So by afternoon session we will see the the fundamental techniques of feature engineering. Okay, because I'm going to take a complete collab file for that. Okay, in that particular the feature engineering techniques, guys, what are all the things we are going to cover? We are going to make a raw data which is suitable for the further process, right? How we are going to make data? It may be some of the data is missing, some of the data is outlier, some of the data is wrong, and some of the data it may not properly collected. So many reasons why the data is actually missing, and it may be a private reason also, right? So what we are going to do now, we are going to make a data which is more suitable for our model or upcoming blocks. That is what we are going to do in the feature engineering applications, right? I will share all the collab file to you. Okay, afternoon session, we will try to cover the feature engineering concepts completely. So what are all the things right now I said now? That is actually the feature engineering. In okay, so how to recover the outliers, how to recover, how to handle the missing data, how to replace the missing data, as well as most of the cases, how to do a transforms on the data. Because already just now I said, if you are having a normal distribution on the data, if you are having a data, it follows the normal distribution. That data actually works well while you are using ML model. Okay, so what we have to do in some of the way, in some of the places, you have to apply some transforms, makes your data into the normal distributed data. You try to bring the data into a normal distribution data, right? We are going to see so many transform. Okay, in the afternoon session we will see that. And right now what I am going to do now, I am going to cover two topics. One is a naive-Bayes classifier for the text classification especially, and another one is a PCA, right? Both the mathematical intuitions as well as I try to map with our applications. So I hope so you people are understand how the mathematics is actually having a strong footage in the ML and as well as the deep learning algorithm designings. I hope so. So here I try to cover all the topics. So my idea is actually I try to map it where it is exactly used. So while you are designing a model, wherever we are actually doing some process, which mathematic operation is much predominantly used to that area. Okay, that is my idea, that is my motive. Okay, we will see that. I try to map in a better way. Okay, so this is actually, this pie chart is I'm showing how data scientists spend most of the time doing a project. I hope so this pie chart is actually enough to explain about so what are all the percentages we are doing. So while you are building a model is only the 3% work, while you are cleaning and organizing a data is exactly the 60% of work, right? It's a very huge work, because once the data gets failed, once your data is not explored the proper way, your model will not work, even if you are design a very powerful ML algorithm. Especially if you are design a random tree, or if you are designing an ensemble learning technique also, it will not work, especially if you are using SVM also, right? Okay, so I hope so you people are understand how the feature engineering, that means sorry, how the mathematical concepts, it's closely related to our ML algorithm designs, and where you have to concentrate more to improve your knowledge in case of ML algorithm, right? So quickly we go through the two more topics. One is a name-based classifier and another one is a PCA, that is a dimensionality reduction techniques. Patient example again. Okay, Bayes theorem. I have a question regarding sign language recognition by eigenvectors. Yes, I am working a sign language recognition system, but not found any practical method of eigenvalue. So could you tell me or share my any document how to find the eigenvalue? Yeah, fine. We will explain. In the afternoon session, we exploit a naive-Bayes classifier for a different text classification as well as a different categorical features. So I don't know what, in which way, what kind of features you people are having. right? So sign language is actually okay, fine. Sign language recognition, either it may be a image or it may be a features. I don't know. Okay, depends on the features only. I can answer your question. Okay, especially while you are using eigenvalue, you can easily identify or you can easily capture the features. Okay, I will clarify your doubt. Right now, I am going to take a naive base. After completed the naive base, I try to complete the PCA. Okay, while I am taking a PCA, you will get an idea. I hope so. Maheshwari, the person is actually asked this question. Actually, while I covering the PCA, you get an idea, right? Patient example. Actually, patient example is actually the person who is coming into that particular hospital. He is having a liver problem, right? So if suppose the next patient is coming into my hospital, what is the chance he is having a liver problem? That is actually that example, right? So the condition is whether the person is having a liver problem, also whether the person is drink where he is having a liver problem also. That is actually the conditional probability we are using to calculate the probability, the outcome probability. What is the percentage of chance the patient who is coming into my hospital having a liver problem in future? That is actually the example, that one. I hope so right now you understand. Okay. Just a minute, guys. I try to share my file. My file is actually not visible. Yeah, naive Bayes. So first I try to cover the naive Bayes classification, and then I slowly move on to the principal component analysis. That is your dimensionality reduction, right? So in this session, what we are going to see, first we will see what is a naive Bayes and the naive Bayes theorem, the mathematical working of the naive Bayes, and then we will see the step by step the programming concept, and then we are going to see how we are the prediction using a naive Bayes, how the naive Bayes is actually used for the prediction applications or a classification applications. Is my screen is visible, guys? Participants, my screen is visible? Is my screen is visible?
Uh, which screen, Suresh? Linear algebra applications.
My presentation, no sir, naive Bayes classification.
No. Naive-Bayes classification is not visible.
Actually, I shared this one.
Visible வருது இங்க வரலடா இது இல்லம்மா our naive-Bayes screen. Suresh, any other screen other than the linear algebra application, something you have put it over the slide, that one or anything else?
No sir, only naive Bayes only actually I am shared sir right now.
Some people say it is visible, but I am not having any visibility over here.
Okay.
Naive-Bayes is visible, some people are putting it.
Yeah, okay,
But
fine,
it is
fine.
not coming from me here.
Okay sir, fine. Shall I continue, sir?
Please continue.
Yeah. So just now we are seeing where the naive Bayes is actually taken. We are actually taken from the third leg of the mathematics, right? It's especially the probability. From the probability topics, we take this naive Bayes classification. That means naive Bayes concepts which is used to design a ML classifier, right? That means machine learning classifier or machine learning model, you can say. So what is really happening in the naive Bayes? So naive Bayes is a simple but spuriously powerful algorithm for the predictive modeling, right? Especially for the classification techniques, we can say. So this is how we are defined the naive Bayes classification. So in this naive Bayes classification, we are having a two important part. One is a naive and another one is a Bayes. So what is exactly the naive? What is a naive? Is there any idea, guys?
Some problem is there.
So without any evidence, or we can say as without any prior training, okay, that is we can say as it is a naive, and the Bayes it actually works based on the Bayes theorem. That is why we say this is actually the naive Bayes concept, right? So we have to know what is exactly the Bayes theorem. Just now I explained there. Okay, just I am trying to give what is exactly the Bayes theorem definition in our ML algorithm. What are all the terminologies which is used in our ML algorithm for using a Bayes theorem concept for classification? Especially we want to know. Okay, so given a hypothesis is actually a, for example, I am telling if you are going to design a linear classifier, right? So what is actually a classification? It try to discriminate the two data, right? Consider data A, data B. So you are drawing a straight line, right? You know, that is we called it as a hypothesis. So that is we says it is a your designed hypothesis, or it is a kind of your rule which is used to discriminate the two datas, right? That is what we are given here. Given a hypothesis H and a evident E, okay, this is actually evidence already we are having. Whatever the data we are having, that is we says it is evidence, right? So Bayes theorem states that the relationship between a probability of hypothesis before getting the evidence, that is we says it is a probability of H. Okay, that is a prior probability. We already know about that, right? And the probability of hypothesis after getting the, what is actually the after getting the evidence? Okay, that is we have to calculate the posterior probability. So far the posterior probability is given it as the maximal likelihood function, which is multiplied with the prior probability and your evidence, probability of evidence. So which is given it as P of H given E is equal to P of E given H into P of H divided by P of E. I hope so you people are very clear with this. What is really naive Bayes theorem works? So if I am going to pick a card, sorry, I am going to pick a card from the deck of card. Okay, so what is the probability of that card may be a king? So how many king is having in the particular card? We are having a totally 4 different kings, right? So out of 52, we are having a 4. So the probability of king can be calculated it as 4 divided by 52. So actually obviously 1 by 30. Okay, likewise. So if my idea is I'm going to pick a card that is actually a king. What is the probability of I'm picking a card as a king, a given face? That means given a face image. Okay, what are all the card having a face image other than the king? Maybe uh, jack having a face, as well as a queen also having a face. Am I right? So this is how we this particular condition we can calculate by using the naive Bayes theorem. So naive Bayes definition, we can given it as the probability of king given face is equal to probability of face given king is multiplied with probability of king divided by probability of face. I hope so you know the how to calculate a probability of face, because how many face images is available right now? Totally 3, right? So 12. So 12 divided by 52 is actually your probability of face, and we know what is the probability of king. So by make use of that, we try to calculate the maximal likelihood functions, right? So this is how the phase given king is actually 1, right? So because at the time we can get only the 1. So far the probability of phase is totally 12. Just now I said, the 4 classes, totally 4 different cards are available in your deck of card. So far the phase is present, it's actually 12 cards: king, queen, jack, and I am not sure the another one more thing. It's a totally, so 12 cards. Yeah, correct. It's a 4 into 3. It's 12 divided by 52, right? So next, what you have to do? We have to compute the posterior probability by using all this probability values. I hope so you people are know how to calculate all those things. This is a very simple application I am exploited for your naive Bayes theorem. Any doubt regarding this? Yeah. So right now we are going to see the proof of your Bayes theorem. So how we are derived this particular equations. So what is the conditional probability? We already have 2 conditions, right? That means the probability of A given B is equal to probability of A intersection B divided by P intersection, probability of B. This is, we are take it from our, both the case are considered as a independent event. Okay. So in the previous slide, in the previous session, we are discussed about this definition. I hope so you people are remember that. Okay, the independent and the dependent event definition, we are seeing this. Okay, so the similar way, if we want to know the probability of B given A, that is also possible, because while you are calculating a intersection B or B intersection A, is obviously it's a similar. Okay, so probability of B intersection A, it's given by P of B. So what I am going to do now, I am going to equate this 2 equations. So what is actually the probability intersection of, because probability of A intersection B, which is equal to probability of B intersection A. From this equation 1, equation 2, I try to find out probability of A intersection B as well as probability of B intersection A. Okay, and then what I am going to do now, I am going to equate these 2 equations, right? So what is the probability of A intersection B? I can write it as probability of A given B is multiplied with probability of B. So probability of A given B is multiplied with probability of B, right? And that similar way, I try to write the probability of B given A, I try to multiply it with the probability of A, right? And try to equate this 2 equation. So look at here, I can come up with the probability of A given B. Okay, so that is given it as, it's actually wrong. It's a, here it should come it as a B. Okay, try to change it one. Okay, so here it's actually probability of A given B into probability of B. This one is actually wrong. I hope so. This is actually B. This is actually A. Okay, so after we are calculating, this is how the theorem proof. Okay, based on this event definition, we try to make use of the 2 equations. We equating this 2 equation, we forms the posterior probability. This is the proof of Bayes theorem. People are understand. This is a self-explanatory one. I hope so, because it's a 2 equation. We try to identify the probability of B intersection A intersection B. Why we are equating these 2 things? Because it produces the same results. A intersection B or B intersection A, it gives the same values. So now that this is actually the definition we are seeing in terms of a machine learning. So we can say this is a likelihood function as a prior probability, probability, and we can also say as a marginal. So all these topics, all these things and all we are discussed in our earlier session. Am I right? What is a posterior probability? What is the prior probability? All the definitions and all we are seen in our mathematical sessions actually, right? This is how the mathematical gives a strong footage of your ML algorithm designs. So now what we are going to do now, okay, now I understand I know one formula, it's already available. How to exploit that formula for my ML application? Maybe that is your question. I hope so. So now, right now, we are going to see how make use of this formula. We are going to act as a classifier, as a powerful classifier by using a naive Bayes classification. We can see that. For this, I try to come up with the some simple problem. Okay, you can easily understand the operation. That's why I try to cover with the simple problem. Always I try to cover each and every topics with the problem. Okay, so that is actually my nature, because while you are seeing the problems, you can easily understand, and if you while you are implementing the algorithm, during that time only we have so many questions. If you are solved a problem, you simply follow these steps in the implementation, you will get a clear idea, you will get a clear picture, right? That's why I am trying to solve the problem here. So in this scenario, I try to take some of the data set, some of the sample data sets. This data set consists, this is a categorical data set, right? Um, so I hope so in the basic class you people are actually exposed into the different types of different data types available in the real-time scenario. What are all the different data types? Maybe the categorical data, nominal data, and your ordinal data, as well as your numerical data. So I hope so you people are exposed in that. Okay, so far this is actually the categorical data. So here we are having three features: outlook, humidity, wind. The fourth one is a target. Whether the player is going to play or not. This is a very famous problem which is always we are used in our academic area to explain about the classifiers algorithm. Especially we are using a decision tree and a naive Bayes, right? So what is we are going to do now? So under the scenario, so first we get the data. Under the outlook, we are having a three classes. What are all the unique thing is present in the under the outlook? Sunny, overcast, rain. So humidity is high, normal. Only two unique things. And what about the wind? We are having a weak, strong. Only the two unique things. And whether the player is going to play or not. So totally we are having a 14 data. Out of 14, 1, 2, 3, 4, 5 data is actually they are not played, and the rest of the 9 is actually played scenario. They are already played. Okay, during the combination, the player is played. Okay, fine. So that means the matches actually happened. Okay, so this is about your data set. So any real-time algorithm, while you are doing, first you have to understand about your data. That is a must. That is the first primary thing while you are doing ML algorithm, right? So from this, what you have to do, especially now, whatever the process we are doing now, that is a common for all the algorithm. So right now, so after this, whatever the thing we are going to see, that is only for naive Bayes, right? What is the first step? You have to transform the contingency table into a frequency table. Okay, how many times it's repeatedly happen? Because by using this category, sunny, overcast, rain and all, we can't manipulate with the Bayes theorem. Am I right? Because we know the formula. If you put the numerical value, then only it works. Otherwise, it will not work, right? So for what I am going to do now, I am going to transform this data into a frequency table. Under this, based on the how frequently it is happened. So that count is we are replaced. For example, I am telling for player is actually yes or no, two classes in the target variable. First, I consider the first features, outlook. Under the outlook, how many types are available? Three different unique things: sunny, overcast, rainy. Okay. Under the sunny, how many yes, how many no is present? We have to calculate. So this is sunny, no. Sunny, no. So you have to count how many no is present. So totally two no, only two no is present. Other than that, everything is yes. Am I right? I hope so. Right? So likewise, what you have to do, you have to calculate the table, right? So if you calculate a overcast, especially overcast, all the value is actually yes. All the value is yes. Okay. And then rainy. For the rainy is a 3 yes and 2 no. So that is a totally, we are having a 5 rainy. So 1, 2, 3, 4, 5. Okay. So out of that, 3 yes, 2 no. Likewise, you have to create the frequent table. Okay. Especially for humidity, that is the second one. And third one is for wind. Okay. The similar way, we have to calculate the frequent table. So this is for first feature. This is for second feature. This is for third feature. So the internal thing is how many sub things are available in the particular feature. I hope so you people are understand how we are formed this frequency table. Any doubt regarding this? Fine. So now what I'm going to do, after the frequency table, I try to calculate another table. It's called a likelihood table. Okay. So the likelihood table, I try to take, so this is my X and this is my, this particular C is nothing but your class. Okay. So the probability, how many classes available in your data set? 2 class, either yes or no. Am I right? Yes. So we have to know what is the probability of yes. So this total value is actually the yes. Okay. So if you add the first column, you get the total value regarding yes. If you add the second column, you get the total value of no. Am I right? So far we need a probability of yes. This is 10 divided by 14. 10 is nothing but what is the total value? Add this first column value 3, 4, 3. So 5, 7, 7 plus 3, 10. So totally 10 values out of 14. How many sample is available? Totally 14 samples, right? What is the probability? You just recall the definition of probability here. Based on that, we calculate probability of C under the yes, under the class yes, it's given it as 0.71. And what are all the things is we need to know? What is the condition here? If my class is yes, given sunny. Okay. If the class is yes under given sunny, what is my probability? Class is no under given sunny, what is my probability? This is what we have to calculate, right? For this calculation, first write the formula and then you try to calculate the values from the likelihood table. That is what you have to follow, right? First, what is the thing we required? Probability of yes given sunny is we need to calculate. Okay. So the scenario, this is our test case, guys. If my probability is the, so if my scenario is sunny, whether you are going to play or not, this is what we have to calculate first. And if my probability is sunny, what is the probability of your not playing? Okay. So far, so probability of sunny given yes, you have to calculate, that is from the table. So only you have to consider the first row value. Here I am given the arrow mark how to calculate the values. It's a self-explanatory one. So probability of x given C is given as probability of is a sunny given yes. Sunny given yes is given it as 3 divided by 10. It's totally 0.3. Same way we have to calculate the probability of sunny. How to get the probability of sunny? You have to add the first row, because this first entire row is about sunny. Either it is a played or not, that is not an issue. We have to know what is the probability of sunny. So far, it's simply we calculate the probability of sunny. So it is 0.36. So we are having all this value put in together, try to identify the probability of yes given sunny. Similar way, you have to calculate for probability of no given sunny. Look at here, what is actually the probability? So this is how you have to know. This is how the implementation part comes here. In the implementation part, you have to identify the argument max, which means which class having a higher probability. That is what we have to identify. That is our class. So your classifier classifies that particular class, right? So out of this, if you are checking, out of this condition, if you are checking, so probability of sunny means the 59% the chances the match is going to held. Okay, if it is a the 40% only the chance it is not going to held. Okay, so what you have to take a decision, you have to go with the yes. Whenever you are exposed with the only sunny, you go with the yes. Okay, this is concerned only the one features, guys. That is very, very important. You try to understand that. It is, we are considered only the one feature. Likewise, what you have to do, you have to calculate the likelihood table for humidity as well as likelihood table for wind. Okay, so based on this, this is your test data. Based on this scenario only, you have to calculate whether they are going to play or not. Okay, so outlook condition is rainy, my humidity is high, my wind is weak, whether the player is going to play or not. This is a test phase. Okay, during the training phase, what it does actually, it calculates this 4 value. The naive Bayes classifier simply in the training phase, it simply calculates the 4 value. That's it. It doesn't do anything, right? It doesn't changing anything. It doesn't forming anything. It simply calculates the 4 values, probability of the posterior probability, and then we are calculate the maximal likelihood, we calculate the evident, and we calculate the prior probability. That's it. Nothing more than that. Okay. That's why we say it is a very, very, very simple algorithm. So now we will see how to, so I hope so you people are understand this one, how to form this table. Likewise, you have to do it for overcast. Likewise, you have to do it for rainy. Okay. So what is the condition, whether they are given to test the classifier? My outlook is rain, my humidity is high, my wind is weak. What about the condition, whether the player is going to play or not? This is how you have to calculate, right? How we are going to calculate this one? Very simple. We know the probability of outlook for the yes. So it is a 2 classes, right? Here I am going to calculate 2 classes. So what is the condition, guys? The probability of, sorry, the probability of outlook is equal to rain given yes. So this is a conditional probability, right? So first case, it's a rain given yes condition. For a humidity, what is the probability? High given yes. The probability is high given yes. What is the next one you have to identify? Weak a given yes. Okay, so this is how you have to calculate. This is the conditional probability. In the previous case and all, we are having a only one features. That's why we are calculated the one posterior value. Okay, one posterior value. But in this case, we are having a 3 features. So far, we simply multiply the values. That's it. In the probability, what you have to do, you simply multiply the features. That's it. You simply takes the outlook feature, humidity feature, and wind feature. So you have to calculate probability of rain by S. What is the probability of rain by S? From the likelihood table, you can easily calculate, right? Probability of rain by S. Okay, fine. We have to calculate this one. Probability of rain by S, you have to compute. So whatever we here I computed, guys, similar way you have to compute. Okay. What here I computed sunny. Similar way you have to compute for overcast and rainy. So once if you compute that, from the value you can easily take the outlook is equal to rain given yes. So this value is 2/9. We will see how to take this value. If it is a sunny and given yes, am I right? That is actually the, sorry, what is the condition? Rain given yes. So rain given yes. So probability of rain, so that is you have to calculate. Okay, right. So I am calculate only for a sunny. Okay, okay, fine. So you have to calculate this value, and simply for the humidity is high given yes. It's actually high given yes. You have to simply calculate it. and wind is weak given yes, okay, into probability of yes. Okay, so this actually, it's similar to your formula, right? What is in the base formula? Probability of A given B is equal to, what is here, the probability whether the player is going to play yes for the given three conditions: rain, high, weak. Am I right? Probability of yes given three things: rain, high, weight. So for a rain, this is a definition. For a humidity, this is a definition. For a wind, this is a definition. You have to multiply the three things. Okay, the formula is given only for the single value. If it is a feature, if it is a vector, you have to multiply it simply. Why I am eliminating the denominator? This is a most important one while you are concerning the implementation part. Why I am eliminating the denominator? What is actually the denominator in the case? My calculation is probability of yes given these three things, right? So what is my denominator? Why we are eliminating? Both the case, both the yes and as well as the no, my evidence is similar. That's why the denominator is a constant. I may eliminate the denominator. Okay, so far if you calculate this value, so which one is the highest value out of this? This is for probability of yes given rain, high, weak. This is probability of no given rain, high, weak. So which probability is higher? What is our rule? What is our final rule? You have to identify the argument max. So which is the maximum value out of this two? Yes is a maximum value. Probability of yes is a maximum value. So the player is going to play. So probability of yes. So the going to play. So our model predicts that 55% of chance there will be a game tomorrow. This is how we have to compute the probability of yes or no under given conditions. See guys, here it is actually simply they are given probability of yes. It's not only yes given these three values: rain, high, weak. So it's a conditional one. It's a posterior probability, right? It's a P of yes given the condition rain, high, weak. I hope so you understand. So now we have to see what are all the different naive-based applications in our day-to-day life. So one of the biggest application is news categorization. So in today's news channel, they are collected the various news from the various across India, right? So that news, it may be a different category. It may be a national, it may be a international, it may be a sports, and it goes on, right? So likewise, we have to categorize it. How we are categorizing this? By using a naive base? That is actually the big question mark, right? Very simple, guys. I am giving a very clear idea. If it is a sports, okay, in the particular data, you're having a word like win, play, uh, win, play, and then some sports related words: cricket, hockey, football. Likewise, you having a words, right? So based on that words, availability of the words, we are trying to classify the documents, whether it comes under the national, whether it comes under a international news, whether it comes under a sports, whether it comes under a media. This is how the naive base works. So naive base takes the bag of words, it try to give the weightage of each and every words for the classes, okay, and try to makes the prediction whether the data is comes under a national or international or sports. Spam or not spam? Once again, it is similar to what we are discussing here. Instead of the news data, here we are concerned with the mail, email. So what is naturally in, if you people are look at the spam, you can see the spam mails and all, it looks quite similar. So what are all the words it's actually presented? Lucky drawn, chances, you won the prize, 1 lakh you got it. So likewise the words are present, right? So naive Bayes classifier identify, that is actually the features. That is actually the feature, guys, right? So that feature, based on that features, it classifies the mail as a spam or ham. Ham is nothing but a non-spam. Okay. So naturally in our Gmail and all, this naive Bayes classifier is predominantly works to classify the spam and non-spam. And moreover, the search engine is most of the text classifications, they are using the naive Bayes classifiers because it is very simple. There is no complication in the particular naive Bayes classification. That's why we are following the naive Bayes classifiers, right? And most of the face recognition application and object recognition applications, we are used to this naive Bayes classification, and especially in the medical diagnosis. Yes. So whether the patient is diabetic or not, whether the patient having a lung cancerous or not, based on their past histories, based on their past features data, right? We are going to calculate probability of yes given feature values, probability of no given feature values. So we have to calculate the values. Based on that, we will compute the argument max. So which probability is higher, we go with, we takes the decision based on the maximum value. Okay, this is how the naive Bayes is worked in the medical diagnosis applications. And especially this naive Bayes classifier is mostly used for the weather prediction also, right? So we have taken the previous datas. Okay, we arranged in such a way, we takes so many features like, you know, wind, humidity, atmospheric pressure, water, sunrises, sunsets. These are all the different features which is taken from the weather data, weather report data, right? So based on that, we try to calculate the probability for rain is coming or not by tomorrow. Because you people are know, India is naturally based on the backbone of India is actually agriculture, right? So agriculture is directly suffered with the weather conditions. So to identify the weather condition is very important, guys, in our day-to-day life. Because even if we are come up with a very good model also, it's very tedious to predict the rainy conditions. That means the weather conditions. So this is how we are discussed in the previous cases. What are all the types of naive Bayes available? So Gaussian, multinomial, Bernoulli. So Gaussian, it works with the continuous data. Whenever we are working with whenever we are having a continuous data. Multinomial is actually, we are having a categorical. Just now whatever we are solved, you know, that is actually comes under multinomial. Okay. So Bernoulli, it's actually, it takes only the binary classes. So afternoon session, we will see the PAMA diabetic testing data, how to classify the PAMA diabetic test data by using a naive Bayes classifier. This is how we are going to see the implementation part. So what are all the steps we are using in this case? We have to handling the data. Once if you take the data, we have to exploit the data. We have to check the data whether the any point is missing, any value is missing, any feature is missing. We have to replace. We have to make the data suitable for the further process. That is we have to do. That is our first step. Next, what we have to do? We have to summarize it. Once if we are finalize the data, we have to summarize it. And next, you are going to make a prediction. You have to calculate the, first you have to form the contingency table. From the contingency table, you have to form the frequent table. From the frequent table, you have to form the likelihood table, right? So making all the predictions. So this is for one features, whatever we have done right now. Likewise, we have to complete it for all the predictions. Next, you have to evaluate the accuracy. Once if we are making all the predictions, we have to evaluate the accuracy of the model. And then finally, we are trying all together, it produces a complete ML model for your PAMA diabetic classification, right? We will see this implementation in afternoon. And this is a some tips to improve the power of naive Bayes. Even though if so many people are aware about this naive Bayes classification and the implementation of naive Bayes classification, try to concentrate on these points. This is very important points regarding the naive Bayes. So first one, if it is a continuous feature, it does not have a normal distributions. So what we have to do, we should apply the transforms. This is we will see in the feature engineering, guys. Right now I said no. If the data is actually follow the normal distribution, that is actually good for any ML model, right? So what we have to do, we have to make the data to bring the normal distributed one, right? If suppose the data is not distributed in the not obeyed in the normal distribution, what you have to do, you have to apply some of the techniques that brings the data into a normal distribution. By afternoon we will see the different transforms which makes the data into a normal distribution, right? That is the first tip. Second tip is zero frequency issue. While you are doing a text classification, this maybe arises. Let us consider your what is your formula? P of A given B is equal to P of B given A into P of A divided by P of B. Am I right? In some cases, in some scenarios, it may be, who knows, the probability of A it becomes 0. That particular point is maybe not available in your text. Okay, there is a no value which is presented in the text. Okay, so what happened during that part? The value, totally the value becomes 0. So 0 into maximal likelihood function, it's also nearly 0. So to avoid that, in your formula, we try to add a 1 plus 1. You put a plus 1 to avoid the zero frequency issue. That is, we called it as Laplace correction. During the implementation time, we will see this. And moreover, while you are working with the naive Bayes, you have to remove the correlated features. This is also we will see in the feature engineering, how to remove the correlated features. Whenever we are working with the data, first we have to remove the correlation. Okay. And the last we can say is the naive Bayes classifier. The naive Bayes classifier has a limited option. This is a very important point, guys. Why today actually I am not covered the ensemble learning or any other thing, because while we are concerned with the decision tree, it has so many parameters to tune. But in a naive Bayes, we are not having any type of parameters. We simply calculates the 4 values. That's it. If you give any scenario, it simply calculates the 4 value from the likelihood table. That is how the naive Bayes classifier works, right? So I don't know whether I rushed this particular topic or not, or if people are having any doubt regarding the problem or any doubt regarding the calculation part, you just ping the message in the chat box. Shall we move on to the other thing?
Suresh, I think it's about to be 1.
Yeah.
Yeah, so that afternoon session, you can make it out accordingly.
Yeah, okay, sir.
Okay.
Yeah, sure,
if
sir.
there may be 1 or 2 questions if you can take it up. Otherwise, you can take it up in the afternoon session also.
Yeah, sure, sir. I just discuss 1 or 2 minutes, sir, and then
okay.
just leave
2
it
minutes
exactly.
You can take it up because 2 minutes are left over. You can take it up, please.
Yeah, fine. Yeah, so one of the Prabhu Ram Nagarajan is actually maybe some problem in my data. That maybe my while I'm making the slide, it maybe I created some problem. That's why that value is maybe changed. Any doubts, guys? Kindly ask your doubts. You put in the chat box. I'm seeing the chat box right now.
Okay.
Can you explain the math behind the multinomial naive Bayes? Yeah. See, actually, whatever we are calculating, that itself, it is a multinomial. What is actually Gaussian? Whatever the probability is calculated by using the normal distribution formula, that is actually Gaussian. The multinomial is whatever we are following, the conditional, the 3 thing is we are multiplied right now, right? So that is actually the multi-nominal naive Bayes classifier. So that is actually the multi-nominal. In the Bernoulli model, actually we concerned with the features are only binary features. Whenever you are having a binary features, during that time only the Bernoulli plays a vital role. Sorry, binomial. A binomial, it's only a 2 classes. Multi-nominal means it is a multiple classes. Hey guys, a small error in my PPT. I will correct it and I will post it in your classroom. Okay. No problem. Okay. So in text classification, yeah, I will show the afternoon. I will show one PPT regarding a text classification. Actually, I designed a separate PPT for a text classification. It takes 77 slides. That's why I am not posted that one. This is a simple explanation regarding a naive Bayes. If possible, I try to cover that particular PPT. That is very simple to see, right? And moreover, I will send that PPT also. You just kindly go through it. It is a self-explanatory PPT. I put all the concepts in that particular thing. The text data is also, I pasted that, as well as I calculated each and every values, unigram, bigram, trigram operations and all. I pasted in that particular PPT. If time permits, I will go through that particular PPT also in end of the session. In this, we need to know the frequency in advance before executing user naive Bayes. Yeah. While we are giving the test data, it calculates the value based on that. Yeah, sure. I will actually, my plan is going to explain about the text classification only, guys. But in the morning session, I took so much of time to explain the mathematical concepts because that is much important, guys. While you are going to read a ML algorithms or ML subjects and all, this places you have to concentrate more. Yeah, sure. I will explain the mathematical concepts behind the text classification. No problem. Actually, I solved the problem regarding that. The bag of words concepts and all entirely I calculated. Afternoon, I will show the PPT.
Shall we take a leave, Suresh?
Yeah, yes, sir. Shall we wind up the session, guys?
We will meet you by 2:30 again.
Yeah, sure, sir. Thank you, sir.
Thanks a lot. And thanks a lot, participant. We'll meet you again by 2:30.